So there's a few things to understand when we're going from a real picture to our circuit diagram. So obviously this is a cartoon, it's not an actual picture of a circuit, and an actual picture of a circuit can make it very challenging to see what's going on. So we're normally going to work with these sorts of cartoons. But now we want to go from this where you see that we have a capacitor, a battery, and a resistor, a couple of wires, and we want to make a circuit diagram. So there's a few things to notice here. First, we have three components here. We're showing three components here. But our battery here on the left was in the middle, and now it's on the left. It's typical to show the battery on the left just so that it's really easy to define the starting point of our loops. So that's kind of a normal thing, thinking about reading from left to right. So in general, put your battery on the left. It doesn't matter that the battery was in the middle. What's important is that you preserve the connection. So note that the positive side of the battery, which is here, is connected both to the capacitor through a wire and to the resistor. So I should be able to draw a path directly from the top of the battery, the positive side of the battery, to both the resistor and the capacitor. So in this case, I can see that I can go to the capacitor and I can go to the resistor. It doesn't matter that here that there's two wires and here there's only one wire. That isn't actually important. So what's important here is that the positive end of the battery is connected to the capacitor and the resistor. Then you follow the bottom and you see that we have a path from the resistor back to the battery, resistor back to the battery, and the capacitor to the resistor. So that's actually this path. But what you should know is that here those wires are connected together, so that's why it's okay to have that. So one of the values in having a circuit diagram that's this simpler geometry is that you see that these two components are in parallel. When in this left picture, you'd be like, I don't know, we have a battery and some stuff connected by a bunch of wires, but this is simpler. So try to simplify your diagrams as much as possible, but you don't want to make them incorrectly. So for instance, had I drawn it as the battery, that's my plus, through the resistor, through a capacitor, back to the battery, well, that is fundamentally a different circuit. That is not the same thing as this, because that actually shows the resistor and the capacitor in series, which is not the case. So make sure that you're drawing the correct circuit to then analyze, not a different one. Another category of items that you're going to see in circuit diagram are meters. And in this picture, you notice that there's an A in a circle. Well, that is your ammeter. And the idea of an ammeter is that it's measuring the current that's going through it. So that's something that we're going to learn about in a later video, but I wanted to at least introduce you to the symbol here. Another symbol you might see is a voltmeter. I don't have one in the figure here, but that's going to look like a V in a circle. V for voltmeter. And the symbols used might vary a little bit. For instance, sometimes you're going to see these little arrows on it, but what's important is that you look for the V for voltmeter, A for ammeter. So I've mentioned before that you want to simplify the ways that things are connected together and that you don't want to actually connect your items together incorrectly. So this is one of the questions from the book, but I think it's a really nice question to analyze and to show you how to think through this. The question here is, of these four circuits, what ones are actually equivalent? Now, obviously, if you just look at them, they all look different. However, if we were to analyze them, we would get the same current, the same potential difference across the components for some of these. So from a physics point of view, some of these circuits are functionally identical, even though geometrically they look a little different. So one way to do this is to start at the battery. Again, in general, it's helpful to put it on the left, but nothing's wrong with putting it in the middle. And you want to follow through and see what it connects to. So in this case, I hit a resistor. I don't have a junction, remembering that a junction is where something splits, but here I hit a resistor. In this first case, again starting at positive, I come here and I hit a junction. And it's helpful to think of a junction as its own sort of not quite component, but it's a symbol. It's something meaningful in the circuit. In B, I again come up and I hit a junction. Now D is a little bit tricky in that our battery isn't in on the left, it's in the center. But again, I come up and I hit a junction. So you can see that 3 of them hit junctions, but C does not. So this one isn't necessarily wrong, it just doesn't show the same circuit that the other 3 do. So now we want to ask if the other 3 show the same circuit. So we're going to start at our junction, and we now have 2 paths. One path goes to a resistor, and I see that in this one, in B, one path also goes to a resistor, and in D, one path goes to a resistor. I'm now going to use a different color, blue, and show that the other path goes to a capacitor. In B, the other path goes to a capacitor. In D, the other path goes to a capacitor. And remember that the battery is the only one that has an orientation that matters. So last, we see that the capacitor goes back to a junction, the resistor goes to the junction. Here, my capacitor comes all the way around to the junction, resistor to the junction. Here, resistor to the junction, capacitor to the junction. And then last, back to the battery, back to the battery, back to the battery. So actually, A, B, and D show the exact same circuit. So it doesn't matter in A that the capacitor is in the middle and the resistor on the right, where here the resistor is in the middle and the capacitor's to the right, but up a little bit, and here it's in this weird triangle shape. So those don't actually matter. A, B, and D are all the same, and you can kind of think of this if you had beads tied together on some sort of stretchy elastic string, that you could actually take those beads and turn them about, pull them into different locations. But all of these are equivalent as long as you're not cutting the string or tying new knots in the string. So that's what's happening here. A, B, and D are actually the same.